Hello everyone, and welcome back to another video. In today's video, we're going to be talking about geometric probability. So we're going to be taking things back to where we left off with probability, but this time we're going to be looking at a different or a specific type of probability, which we call geometric probability. And the math in this video, and the formulas aren't going to be necessarily complex or even that hard at all. It's more about the concept of figuring out when to use geometric probability, and then sort of how to apply it. But the actual math, I think we will find to be pretty straightforward. But let's get into sort of a general example of what I mean when I say geometric probability, because we're used to saying if there's 7 marbles and 2 of them are red, what's the probability that you pick a red marble? And it would be 2 over 7, and that's not geometric probability. But let's take a look at an example which would classify it as geometric probability. So the simplest example would be a one-dimensional problem. So that would just be a line. So for instance, let's say that we have some number, let's say capital X, and X is going to be a random number between 0 and 3. And our question is, what is the probability X is closer to 0 than it is to 1? So there's infinite possible outcomes for X, because we'll say that X is a real number. A real number would just be any number that has decimals. So 3.74321 is an example of a real number. But X is between 0 and 3. And we want to know the probability that's closer to 0 than it is to 1. So what we can do is we can draw a number line. So this is a very simple example of geometric probability. And so we'll start at 0 because that's our least value, and 3 in this problem is our maximum value that X can be. And we'll also draw the number 1 because we want to know, well, what is the probability that X is closer to 0 than it is to 1? Well, where is it the same distance? Where is the distance the same to 0 and the same to 1? Well, that would be split in the middle. That would be at 0.5 right here. So basically, then we can realize that, oh, well, X is going to be closer anywhere less than 0.5. So that's this segment right here. So now we can use geometry. It's a very simple geometry problem, but we see that, oh, well, this blue little segment that I just drew, how many are those in our total interval? Because that's going to be the denominator. So how many of these blue little squiggles would fit? Well, we fit 1 in 0.5, from 0 to 0.5, meaning there's going to be 2 of these from 0 to 1, meaning there's going to be 2 times 3 of them total, so that would be 6. Because that's the number of intervals that are 0.5 length. But we only care about this one right here, because that's the only one where X is closer to 0. So our answer is going to be 1 over 6, because our only interval that's of 0.5 length is from 0 to 0.5. Because once we go from 0.5 and on, X is just going to be closer to 1. If we choose X right here, it's closer to 1. If we choose X here, it's closer to 1. So that's a simple example of how we can use geometry to solve our probability problems. But now let's look at a two-dimensional geometry probability problem. Okay, so this problem says a dart is thrown at a circular dartboard such that it will land randomly on some area of the dartboard. What is the probability that it lands closer to the center than it does to the edge? So this reminds us of the last problem, as we had the number X and we wanted it to be closer to 0 than 1. But here it's an area problem, essentially, because we're going to have to draw a circle. Okay, so I've drawn a circle, and as you see, I've actually drawn 2. So what we might have realized is this circle, the inner one, the blue one that I'm moving around, is the area in which our dart lies closer to the center. So anywhere outside of it, any of this range, the dart is going to be closer to the edge than it is all the way to the center. Of course, we don't know. Well, we're asked to find out, what is this area of this blue circle. So how can we begin? Well, first, since it's a probability problem, we know our answer is going to be a fraction. And our denominator is going to be all possible outcomes. So in that case, all possible outcomes of where the dart could go is just the total area of the big circle. So if we say that the area of the big red circle is pi r squared, because the radius is r, that's going to be the total outcomes of all places where the dart could go. So the dart could go here, could go here, and there's infinite possibilities essentially, except when you sort of add them all together, it's going to form this circle. And since we gave it a radius of r, its area is pi r squared, so that's going to be our denominator. But now we want to find the successes, the number of places where this dart is going to land closer to the center. So basically, we want to find now the area of this blue circle. So how can we go about doing that? So just like the last problem, let's find the distance or the spot where the dart is equal distance from the edge and from the center. And as you might realize, that's going to be exactly on this blue circle. And we know this because we made this blue circle ourselves. It wasn't given in the problem. We created it knowing, well, this blue circle and the area of it is going to represent all outcomes where the dart is closer to the center, meaning the border of the blue circle is going to represent distances equal to the center and distance equal to the edge. So what is the radius, therefore, of this blue circle? Well, if the whole distance, meaning the whole big radius of of the red circle is r, half of that is going to be the radius of the blue, so 1/2 r. So therefore, the area of this blue circle, or the good outcomes, we can write as 1/4 pi r squared. And we can simplify this. We see that pi cancels. We see that r squared cancels, so actually the radius doesn't matter, right? And we see 1/4. So we have a 1/4 chance of throwing a dart into this blue circle, essentially. And therefore, we have a 1/4 chance of throwing a dart where it's closer to the center than to the edge. A 25% chance. So in this video, you've seen that the actual math that we had to use was simple. We used an area formula for the circle problem, but it was more about figuring out how we could use geometric probability to solve our problems and sort of how to set up the problem itself rather than calculating an answer. And you'll see that actually throughout a lot of competitive math, as it gets harder, that actually becomes the more complex part, meaning setting up your problem and setting up your solution rather than just calculating it. So that's going to be all for today's video because the actual math isn't that complicated, and you'll sort of get a knack for it. You'll get a sort of technique for being able to develop how to formulate a geometric solution to probability problems. And you'll realize as you just do more general probability problems that certain ones you could do multiple ways, but perhaps geometric probability problems or solutions are a lot easier. So we're going to include, as always, a problem set in the email that we send out. And if you have any questions, you can email us about them because might be a brand new topic. So although the math isn't that hard, it's definitely a little bit tricky to sort of come up with a solution using geometry. And then we'll host a Zoom meeting, of course, to go over the problem set. And there you can also ask questions about geometric probability or any other math that you're interested in. So I hope you guys enjoyed the video and that you try out the problem set and come to our Zoom meeting. As always, thanks for watching, and don't hesitate to send us an email if you have any questions. Thank you. Bye.